So today we're doing section 5.3. You'll notice that we skipped 5.2 for this course, so you guys aren't responsible for 5.2. Notice on the homework set that it jumps all the way to 47, so make sure you don't have to worry about 15 to 45 or 46 or whatever. So make sure you don't worry about any of those problems. So section 5.3 is about proving trigonometric identities. And I know that whenever we say that P word, it gets pretty scary, right? But the proof here that we're going to do isn't like the proof that you did in geometry, because we're not going to cite any theorems or anything when doing this. It's all going to be kind of algebraic. And really, in a way, it's not going to be dissimilar to what we did in 5.1, where we simplified these trigonometric expressions. So along the way, we're going to kind of outline some strategies that we can use, and then we'll do some examples, and kind of that'll be it. There's not a lot of like content. The strategies are all basically just kind of advice or tips or whatnot, and then we'll just do some examples. So the proof is going to begin with just one side of your equation. It doesn't really matter which side you start with, although you can make life easier sometimes choosing one side versus another. And the proof ends when you get the other side. And the steps to go from your starting to your end is what's going to be the proof. So the part that I care about, and the part you're going to be graded on, is that middle part, is the steps going from the beginning to the end. So this is purely a work shown kind of problem. So let's look at an example. And the first example we're going to look at is a simple one in that there's no trig functions involved. It's just kind of like purely algebraic. Then we'll do the rest of our examples will have trig functions involved, but just to kind of get a feel for what's going on initially, we're going to start with something where we only have to worry about the algebra piece and not the trigonometry piece also. Okay? So the first thing we should do is we should pick the side that we want to start with. Now, my typical advice is to start with the more complicated side, because it's usually easier for us algebraically to go from something complicated to something simple. It's typically not as clear how we go from something that's kind of simple and build it out and make it into something complex. Usually algebra is easier for us going kind of downhill than uphill. Does that make sense to you guys? So on this one, it should be pretty clear which side is the more complicated side. If I look at this example, it's the left-hand side. You guys agree with that? Okay. So if I look at this left-hand side, somehow I need to change that into 2. So algebraically, there's a couple of things that I could do here. In fact, I think probably 3 reasonable things that you could possibly do. Let's take a look at this and see if we can figure out the 3 things that I could possibly do. And then we'll talk about which one of those might be the best one to choose in this case. Does anybody see anything that they could do to that left-hand side? Landon.
I mean, like, maybe you could try and get, like, a common denominator.
Great. So we have 2 fractions that are being subtracted. One thing you could do is make a common denominator so you could actually do the subtraction. That's one thing for sure that I was thinking about. What else? That's probably the most obvious thing also. Landon?
Could you, like, maybe distribute the subtraction? Just combine the 2 fractions.
Well, that still would require a common denominator, right? If you wanted to combine the fractions. So when you do distributing the negative, whether it's here or when you're adding fractions, it's still kind of the same thing. But you're right, if we were to add fractions, we definitely have to worry about the distributing the negative, for sure. Tyler?
Okay, so I don't remember if this is subtraction or addition, but can't you, like, multiply them together with reciprocal in the second fraction?
Okay, so that's if you're dividing 2 fractions. Yep. But there is another fraction-related thing that we could do here. What if I were to try to add 3/6 plus 2/4? What might you want to do before you try to add those? Reduce them, right? Now, it's possible these fractions could reduce and might make the addition and subtraction even easier. That's another thing that we could do. And the third and final thing, this is the toughest one, would have been the toughest one to notice, I think. If you look at the numerators of those 2 fractions, what do you notice? They're the same. So you could factor that numerator out, like a greatest common factor, and then just have 1 over x minus 1 minus 1 over x plus 1. You could think about it that way also. Now, amongst those 3 things to do, which one do you think is going to be the best thing for us to do? I would always try to reduce first, because the reducing, if we're able to do it, is going to make the common denominator processes easier every single time. Now, we may not be able to reduce the fraction, but I at least want to give that a chance to do that. Ben? Sure. So, remember back to your Algebra 3-4 class last year. To reduce a rational expression like this, what do we have to do first? This is something we did a lot of last year, so hopefully somebody can remember. There's a step that we have to do before we can do any reducing for a rational expression like this, where you have a fraction involving variables. Starts with an F. And then an A. Factor. Yeah, we have to have these in factored form in order to reduce them. So x squared minus 1, hopefully you recognize that as a difference of two squares. So that's going to factor to just x minus 1 times x plus 1. Everybody okay there? Now, how do these things reduce? Like we factored it. What am I looking for when I go to reduce something like this?
Like a relationship, like the top and bottom are the same numbers almost.
Okay, so the factors in the top and bottom have to be identical in order for me to reduce it once it's in a factored form like this, correct? So in the first fraction, we can reduce the x minus 1s. And in the second fraction, we can reduce the x plus 1s. Everybody okay with that? When I do that division to reduce them, what do they become when I cross them out? They don't just disappear. What do they turn into? 1s. So really I have like 1 times x plus 1 divided by 1. But that's really just x plus 1, right? And similar over here. And look at this. By choosing to reduce first, we avoided having to even find a common denominator at all, because we have no more fractions, which is great. Had you gone and found a common denominator first, you could eventually still get to this step, but the reducing becomes that much worse, because the factoring would have been much more difficult. But wouldn't have been wrong, it just makes it a little harder. Okay, what do I want to do next? Landon mentioned this earlier. Yeah, so to do the subtraction, I have to distribute that negative. Now, the first quantity, I can really just drop the parenthesis because it's just a positive thing, right? There's nothing multiplied to it, so those parentheses don't need to be there. The second parenthesis, though, I had to make sure I distributed the negative through before I could drop the parenthesis. Okay, now what? So I combine the like terms, so the positive x and the negative x add to give us 0, right? When we're adding and things cancel out, they become 0. And then I just have 0 plus 1 minus 0 plus 1, which is just 2, right? And that's equal to 2, which is what we wanted to show. So we're done. That little square at the end that I color in is just like the period at the end of the proof to show the reader that I finished the proof. Ben?
How are the options?
Sure. Let's do another, okay? So on this particular one, everything we did was kind of algebraic, right? So you can still do these same algebraic things. In the trigonometric ones, but you'll also have access to using your trig identities. So that's going to be the difference. So when we start with these trig identities, again, we're going to start with the more complicated side. And when I say complicated, what I typically mean is has more terms. So for example, if I have x plus y on one side and x times y on the other, x plus y is the more complicated because it has two terms, two things are being added, as opposed to the other side where it just has one term. Even though two things are multiplied together, it's just one thing, right? Like we think of 2x as just one thing. So keep that in mind, that addition is kind of more complicated than multiplication. If you get stuck or you're not sure what to do or there's nothing algebraic to do, I typically would advise to convert everything in terms of sine and cosine. And then make sure to use a common denominator if you're going to add or subtract fractions. So let's take a look at our next example. Here we have tangent of x plus cotangent of x equals cosecant of x times secant of x. Which side is the more complicated side here? The left or the right? The left, because you have two things being added together, as opposed to the right-hand side where you have one thing, because there's no addition or subtraction going on at all. So let's start on the left-hand side. So if I look at cotangent of x plus, tangent of x plus cotangent of x, is there anything algebraic to do? No, right? There's no fraction, so we can't reduce or use a common denominator. There's no like terms to combine. There's no greatest common factor to pull out. So there's nothing algebraic I can do with this. So I know that whatever I'm going to have to do on this first step, it's going to have to be trigonometric. Does anybody see anything obvious to do here? Landon?
You turn cotangent into 1 over tan, and then make tan over 1.
You could do that. I would probably, though, in this case, just convert them both to sines and cosines, since you're going to end up having to make a common denominator with fractions anyways. It's probably going to be a little bit easier if I do that instead. But that's not a bad idea, what you're describing. So if I look at Q1 on my identity sheet, tangent is sine over cosine. And if I look at Q2, cotangent is cosine over sine. You going home, Ben?
Yeah.
Hope you feel better.
Thank
So that's what I did there, is I just used identities to rewrite both of them in terms of sine and cosine. And Landon, what you had suggested would have been okay also. I think it would probably end up getting a little bit messier, but you still would have worked. You didn't suggest anything that was wrong. Okay. What should I do next? I have two fractions that are supposed to be added. There's really only one feasible thing to suggest here. Make a common denominator and add the fractions. Okay? So my first denominator is cosine of x, and the second denominator is sine of x. What would the common denominator there be? Okay, so let's ask this question first then. If I have 1 over 2 plus 1 over 3, what would the common denominator be? 6. Because it would just be 2 times 3, right? Because there's nothing in common between the 2 and the 3. Right, there's no factors in common. So here, are there any factors in common between cosine of x and sine of x? No. So what should the common denominator be? Cosine x times sine x. Does that make sense to everybody? So the first fraction will multiply by sine x over sine x. And the second fraction by cosine x over cosine x. That feel good? Okay, when I do sine x times sine x, that gives me sine squared x. When I do cosine x times cosine x, that gives me cosine squared x. And then my common denominator just stays the same, so I have sine x times cosine x as my denominator. Does that feel good to you guys? What should I do next? Landon?
Do you want to look at your
Great. So Landon sees that sine squared plus cosine squared is one of the Pythagorean identities. That is equal to just 1. If you don't have your identity list out while we're doing this, it might be helpful if you're following along, if you're looking for suggestions, to have that handy so you can look at it for reference, because I don't expect we have these things memorized. So far, so good? Okay. Now, if I look at what I'm supposed to be getting, I'm supposed to be getting cosecant times secant. So that's the product of two things. Everybody see that? What I have right now is a fraction, a single fraction. What I want to do is rewrite this so it's the product of two fractions. So I'm just going to rewrite this as 1 over sine x times 1 over cos x. Landon?
You re-explain, like, how do you know?
Yeah, when I looked at what I'm trying to get to, it's the product of two things. But I have only one fraction. So I said, okay, what if I just write this fraction as the product of two fractions? Since I have a product in the denominator, I can do that really easily. Does that make sense now?
Yes.
Okay. And that's a trick that's not uncommon. Everybody still on board? Okay. And if I look at my identities now, I notice that 1 over sine x is cosecant x, and 1 over cosine is secant x. So now the two sides are equal, and I'm done. Landon?
So, like, on the test, you want us to write that, like,
That part's not super duper necessary. I'm just always going to do it because I'm used to doing it. I get excited to write it down because you finished your proof. And these aren't super easy. I mean, they're super easy for me, but like they shouldn't be super easy. You should be excited when you finish one. It's like, yeah! Exclamation point. Got it. Okay. You guys ready to go to the next one? So some more strategies that are often helpful on these trigonometric proofs is the difference of two squares factoring pattern is your friend. And then my other strategy is to always keep in mind where you're trying to get to, right? Keep in mind what the other half, what you're trying to get your one side to become. Oftentimes that'll give you some idea of like, hey, look, I already have this part and this part straightened out. So I know that this stuff has to turn into this thing. And it can kind of give you some intuition as to where to look for what you might need to still do. I just simplified that by saying eye on the prize, right? Like, keep in mind where you're trying to get to. Okay. So let's look at the example problems here. So the first one, we have 1 over secant x minus 1 plus 1 over secant x plus 1 equals 2 times cotangent x times cosecant x. Which side is the more complicated side? The left, because it's addition. Everybody's good with that? Okay. So let's work on the left-hand side to start. What do you suppose, all right, algebraically, is there anything to do? Typically, I like to start by looking for algebraic things to do. You have two fractions that are being added. Common denominator time, right? So if I look at secant x minus 1 and secant x plus 1, those are my two denominators, what would the common denominator be? Jane? Very good. That's correct. So notice again, there's no common factors in between them because of the plus 1 and minus 1 stuck to the end, because that's part of a polynomial. We know that we have to think of that as all one thing. So they are definitely different. So the first fraction, we're going to have to multiply by secant x plus 1 over secant x plus 1. And in case you haven't figured out my color coding, the red stuff is the previous problem that I didn't change, and the blue stuff is the stuff that's kind of like changing or whatever, right? And to the second fraction, we'll multiply secant x minus 1 over secant x minus 1. So I distribute the 1 through, but that's no big deal. And then my denominator just stays the same. So far, so good. Okay. Do we see anything algebraic to do? I see a couple of things algebraic to do. I wouldn't do any. You can't actually do any reducing because those are being added and not multiplied, right? If it was secant x plus 1 times secant x minus 1, then you'd be able to do some reducing. But since they're being added, we can't do any reducing there. But there is a bunch of algebraic things we still can do here. If you look in the numerator, there's a bunch of like terms we can combine, right? So I have a +1 and a -1. Those can just cancel out to give me zeros. So they just kind of go away. And if I have secant x plus secant x, that's going to be 2 secant x, because we're adding, right? Just like x plus x is 2x. And then the denominator, I would FOIL this out. Now, personally, I'm going to notice that this is a difference of 2 squares. I have like a plus b times a minus b. So I'm going to just use the shortcut and just say that's a squared minus b squared. Or really secant squared x minus 1. Now, if you FOILed that all the way out, you'd end up at the same spot eventually, but you'd have a little bit of more reducing to do. And I'm going to start a new column over here because I'm running out of space. Okay. So here, is there anything algebraic to do? No, right? Now I wanted to ask that question to make sure that we're not saying that you can reduce here. Why can't you reduce there? Not because of the 2. Multiplication is okay to reduce. It's because of the -1 in the denominator. You can't reduce part of an addition or subtraction problem. You can reduce part of a multiplication problem. So that's the issue why those couldn't reduce. If it was just the secant squared in the denominator and there's no -1, yes, we can reduce. Everybody's okay with that? Again, these little algebra things is part of the reason why we're going agonizingly slowly through this, is so that we have a chance to talk about these things. Okay. So if there's nothing algebraic to do, what should I look for? An identity. Okay. So take a look at your identity sheet. So the piece that I would really want to get taken care of is in my final answer, there's no addition or subtraction going on anywhere, correct? I would want to see if there's a way to get rid of the addition or subtraction going on in that denominator. What is our only identities that involve addition or subtraction? The Pythagoreans. So what I would do is I would note that in P3, I can replace the secant squared with tangent squared plus 1. And I'm digging that because I have that -1 at the end that's going to gobble up that +1. Which I'm pretty excited about because that has now accomplished exactly what I wanted it to. So far, so good. Okay. So if I look at what I'm trying to get to, I have the product of 3 things, right? I have 2 times a cotangent x times a cosecant x. So what I'm going to want to do is I'm going to want to try to rewrite this as the product of 3 things. So I can do 2 times secant times 1 over tangent squared. Does that make sense to everybody? Now again, if I look at that final piece that I want, I notice there's no fractions in that. So I'm going to look at my identities and see if there's a way to replace tangent or 1 over tangent squared with something that's not a fraction. If I want to get rid of a fraction, I'm probably looking at the reciprocal identities in particular, since the numerator of the fraction is 1. I notice that 1 over tangent is cotangent. So 1 over tangent squared is cotangent squared. That's, what is that? Q or R9. Sorry, R9. R6. I was looking at it upside down. Not really. I just don't have an excuse. So far, so good. Now, if I look at, again, what I'm looking for, it's like, hey, 2 cotangent. Well, I have a 2, and I have a cotangent squared. But cotangent squared is just cotangent times cotangent, right? So I'm going to break the cotangent squared piece up. As cotangent times cotangent. And the reason I want to do that is because now I have the 2 cotangent piece. So somehow cotangent times secant needs to give me cosecant. So again, this is kind of the eye on the prize helping me inform what to do. Right? It's very unlikely we'd think to break up cotangent squared if you weren't already looking at the answer and go, oh, I'm supposed to have a single cotangent in that. Well, let's just pull the single cotangent out of there and leave whatever's left. You know what I mean? Okay. So, somehow cotangent times secant needs to give me cosecant. So I'm going to go ahead and look at my identity sheet for things involving cotangent or secant and see if there's any of those identities that allow me to get a cosecant out of that. I see the winner in Q2, that cotangent is cosecant over secant. And that is going to give me exactly what I need to have happen. Since this is multiplications, we can reduce, and now we're left with exactly what we wanted. Now, I took my time kind of going through that because there's a lot of stuff to explain for the first time we're seeing it. I wanted to go slow and not just like bulldoze through this and make it look like it's the trivialest thing in the world, and kind of discuss what I'm thinking in my head and what I'm looking for and what I'm seeing and why that's important. Hopefully this is helpful. Again, we need to develop some intuition as to like what are good things to do and not good things to do, or like what do I do if I get stuck? And I don't know a better way to do that other than just kind of talking through these things slowly and giving you my internal narrative of what I'm seeing when I'm doing these. All right. Let's look at the next one here. So we want to start by looking for the more complicated side. Is there one? They both look about the same to me, right? So here it doesn't really matter which side you start with. For the argument, or sake of argument, let's start with the left-hand side since that feels the most natural, right? Okay. Is there anything obvious to do here? Doesn't seem like it, right? Algebraically, obviously you can't reduce the fraction. There's not two fractions to add. There's no like terms to combine. There's no factoring to do. So, okay, maybe we go look for an identity. Is there any way to turn cosine, regular old cosine, into an addition problem? No. Is there any way to turn 1 minus sine, a subtraction problem with a degree 1, into a single thing? No. Ugh. What should I do here? Well, here's a case where the previous two strategies really are helpful to us. So if I think about the eye on the prize, in the numerator here, I need to somehow get a sign, or 1 plus sign. So one way to do that is just to force that 1 plus sign in there by just multiplying the top and bottom of that fraction by that. And upon further review, I really think this is an excellent idea because what do I see in the denominator? It's a difference of two squares, which is usually a great sign that I'm doing something right. Now, coming up with that trick on your own, having never seen anybody show you that, that's tough, right? Would have been to coming up with that on your own. But having seen it before now, you're as knowing like, oh, that's something to do. If I'm kind of stuck, you know it's possible. All right. So now, technically, this cosine is going to distribute through here, correct? But I know when I look at where I'm trying to get to, the cosine in the numerator needs to cancel out somehow. Everybody agree with that? Because it's not in the final. So my suspicion is it's going to reduce out of there somehow. I don't know how yet, but I'm suspecting that's going to be the case. If I'm going to reduce a fraction, I really want to keep this in factored form. I don't actually want to distribute the cosine through. So I'm just going to write this as like cosine t times 1 plus sine t. And I'm going to write it kind of in that factored form. Now, had you distributed the cosine through, that's going to be fine. You'll just end up factoring it back out later, but I'm going to try to save myself having to do those steps if I don't need to. Is that okay with everybody? Again, I'm trying to explain to you why I'm choosing to do that here when most of the other time we've just distributed things through and not even thought about it twice. And then again, I have 1 plus sine t times 1 minus sine t. If I multiply that out, that's a difference of two squares. So you could FOIL that out, or you could use the difference of two squares factoring pattern to write as 1 minus sine squared t. I chose to use the factoring pattern to shortcut it because, I do work smarter, not harder, right? Okay. So what I'm looking at now, again, if I look at where I'm trying to get to, I need just a single term in my denominator. So my first order of business, I think, is to try to get rid of the subtraction going on in the denominator here, which is now an option because I have something squared that's being added or subtracted. So I'm going to go straight to my Pythagoreans. Which one of the Pythagoreans looks like the one that I'm going to need to use here? P1, because it's involving sines and cosines. So I notice that sine squared plus cosine squared is 1. So I'm going to replace my 1 with sine squared plus cosine squared. Which I love because I already have a minus sine squared in the denominator that are going to cancel those out. So far, so good. And what do you notice we can do now, Landon? Yeah, so I can reduce, right? I can cancel one of the cosines from the top with one of the cosines on the bottom. And that gives us exactly what we were looking for. So far, so good? Well, so far, so it's, there's nothing more. There's no more farther that we have to go. That's the end of that one anyways. How we feeling on these? Does this feel like we're kind of getting a little bit more comfortable here? Okay. Of course. All right, one final strategy. So the final strategy is, if we're working here, if we get stuck on one side, we can jump to the other side and try to work on meeting somewhere in the middle. So that's what we'll end up doing on this next one. Okay. Which side do you want to choose to work on? I think they're basically the same, right? The left-hand side has two things being divided. The right-hand side has two things being multiplied. One of the things being divided has addition going on in it. One of the things being divided has subtraction going on in it. It's basically the same level of complexity. So it doesn't really matter. Let's start with the left-hand side, though. That sounds good to me. All right. Is there anything algebraic I can do with cotangent squared u over 1 plus cosecant u? Sure doesn't look like it, right? There's nothing to reduce. There's only a single fraction. Inside of the fraction, there's no like terms to combine or any factoring to do, so probably identity time. So what I'd be looking for is a way to rewrite cotangent so it has cosecants in it, or the cosecant so it has cotangents in it. And this one's a little tricky because probably what I'm going to use is P2. But I'm going to have to rearrange it a little bit. So P2 says 1 plus cotangent squared is equal to cosecant squared. What I'm going to do is basically subtract 1 from both sides of that. So I can say that cotangent squared is equal to cosecant squared minus 1. Everybody okay with that? Now that's a little bit of a, a little bit sneaky to go ahead and use one of those identities rearranged like that. But the Pythagoreans, it's often helpful to do that kind of thing. Tyler? Of course, yeah. All right. So remember the previous set of strategies. One of them was the difference of two squares is your friend. If I look at the denominator, that looks like one part of a difference of two squares, right? Or one factor in a difference of two squares. If I look at the numerator, I see something squared minus something squared. That is a difference of two squares. So my hope is if I factor the numerator, I'll be able to reduce and get rid of the fraction altogether. Okay with that plan? So cosine squared u minus 1, it does factor into cosecant u plus 1 times cosecant u minus 1. And then I can reduce those two pieces. Now, even though they're in a different order, it's okay because addition is commutative, right? 2 plus 3 is the same as 3 plus 2, right? Cosecant plus 1 is the same as 1 plus cosecant. And then I'm left with cosecant u minus 1. Which is great. I've got rid of the fraction. I know that where I'm trying to get to has no fraction in it, but I don't like my chances of taking what I have there and ballooning it out to be that stuff, right? There doesn't seem to be a lot of obvious way for me to go and make, turn that into the other piece. So I'm going to jump to the right side. And I'm going to start working there and hopefully end up with cosecant u minus 1. Sound good to you guys? If I look at the right-hand side, is there anything algebraic to do to start? I disagree. I think there is something algebraic that would be good to do. I'm going to distribute that cotangent through, right? Because what I'm trying to get to is just this, like the difference of two things. If I distribute that cotangent through, maybe I'll do this side in green or something. I now have the difference of two things. Now I see that one of those two things is cotangent times tangent. I recognize those two things are reciprocals. So I can say, for example, rewrite cotangent as 1 over tangent. Which is going to give me the 1 minus part that I need. So I know somehow this part is going to have to turn into cosecant, right? So I'm going to go and look at my identity sheet and look for a way to rewrite cotangent or secant so that it has a cosecant in it. What I'm going to need is Q2. That cotangent is cosecant u over secant u. And the secants can reduce. Leaving just the cosecant. And I'm good. The two sides are now equal. Even though I didn't go and take the right-hand side and make it the left-hand side, or the left-hand side and make it the right-hand side, I did a little work on each and met in the middle. That's okay for us. If you're in the honors class, we wouldn't let you do this. We'd make you do on one side versus the other. But in this course, we're going to let you meet in the middle there. I think that was our last example here. Okay. The next class is just going to be a work day. So we'll talk about the exam or the test format for chapter 5 and stuff. And let you just spend the class period working on things or take questions or whatever. My suggestion to you is to try to do some of these identity proofs before next class. So if you have questions on things, or you can get a little bit of individual feedback if you need it, but it takes a little bit of time to feel like you're getting the hang of these and getting good at these. So best to try to get a jump on that before next class. And if you haven't been doing that, I would make sure that you have your identity sheet out while you're working on these things. It makes it much, much easier to not have to be flipping back and forth, back and forth, back and forth, to where you can look at the problem and look at the identity sheet and just like move your eyes rather than like turning a bunch of pages or going to a new tab on your OneNote or whatever. And I gave you guys all a physical copy of the identities last or before break, right? When you took your quiz. Okay. Cool. That'll be it for today.